Raymond Chin, a water and wastewater engineer with over 30 years of technical design and project management experience from start to finish of the project cycle. This includes conceptual design, detailed design, cost estimating, construction, and commissioning of water and wastewater treatment systems. Raymond has worked for municipal, mining, petrochemical, and indigenous clients and has experience in treatment, equipment manufacturing, and plant operations. He enjoys solving problems for clients, leveraging innovative technology. History, Jungian analysis, and cosmology. Raymond's currently with WSP and will be discussing the Squamish wastewater treatment plant 2023 upgrades. Please join me in welcoming Raymond.
Thank you, Chris. So, hello, everybody. This morning, I'm going to talk to you about some of the work that I've been doing up at the District of Squamish. I work with WSP, it's an engineering consultant, and we were awarded assignments about 2 years ago to upgrade the treatment plant. Squamish is just located at the tip of Howe Sound there. And it's located at the confluence of two rivers, the Squamish and the Mampram River. The scope of the assignment that was awarded to us was a detailed design of a upgrade to expand the plant. Designing and building an anoxic tank, a blower building, and a septic receiving. So the plant kind of looks like the layout there. The 1996 biological train fire, and then in 2006 a new combined treatment unit consisting of a bioreactor and clarifier. And the project scope envisioned was something like this: an anoxic tank to go with this train, a new blower building, and a septic station to go there. So some context for the project. Back in about 2015, the district had hired a consultant to take them down the path of going down registration with municipal wastewater regulation. At that time, the province was encouraging municipalities to do that. And so as part of that, they did some studies. And in that study, it was determined that the biological treatment capacity didn't have adequate redundancy. When the largest unit was out of service, the second unit didn't provide the requirement for 75% capacity. So that was a recommendation that came out of that liquid waste management planning study. So the district went and took that, and they hired, they put out another assignment to an engineering. In that consultant looked at different options, and they were really in favor of going down a membrane separation path, which it turned out the district wasn't really that in favor of that. So that consultant sort of added an alternative to increase the aeration tank volume, and particularly in the form of anoxic tank volume. So they came up with a concept and a recommendation to do that. The district then took that and put out another assignment to do the detailed design of that, what that recommendation was. And that was the 2020 assignment, which the company, which I got involved in, and our company was successful in doing that. So with that scope, we set into doing that work. It was about a $11.5 million budget to do that. And as the first part of that process, in the pre-design work, we did a project concept review to to see. Looked at the operations. Plant evolve over the years, and what were the different designers thinking as the plant evolved, and also looked at long-term considerations for future build out of this plant. So just to summarize, out of all that preliminary design work, these are some of the situations and conclusions that we came up with. That there were many expansions over the past 50 years, and creative engineering solutions by various designers were employed over all that period to reuse infrastructure and adapt it and do it at a low cost. And it was very creative, but as a result of that, it ended up with a real patchwork of different systems that were hard to further expand. Also, there was quite a large turnover of district staff within the engineering group, within the operations group, even within our project scope period. There was like 2 senior operators who came in and left. So that makes it challenging with turnover. And we identified that the existing project, the agnostic tank, carried a number of concerns, and maybe it wasn't the best approach to take. Finally, seismic liquefaction is a significant concern in this plant area. And with the new building codes and seismic conditions, it sort of drove some decisions that maybe were different than what was originally envisioned in the detailed design project. I'm just going to take you through a bit of a history lesson of the plant that we unearthed through the investigation. Back in 1972, the district had 2 treatment plants, one at Central, this is downtown, and one up at Mamquam. And the Mamquam plant is the one that we're talking about in this assignment. Both the original plants were similar to this one here at Mamquam. It had an aeration tank that was fed by a screw lift pump station. And after the aeration tank, it went to clarifier cells and then to sludge digesters on the outside. Sludge went to a sludge drying pond, and the effluent went to a chlorine contact tank and then out to disinfection. And the control building was located here, and that was how the operators kind of managed the facility. The plant was rated at 4,500 cubic meters a day. And this operated for quite a number of years in both those facilities. And then in 1980, the same engineer that designed the original facility did an expansion upgrade that, well, it wasn't an expansion, it was an upgrade. Gravity thickener was installed up in the right-hand corner, and a screw press was installed. And so the sludge was thickened and then dewatered with a screw press. And then in 1996, another consultant got involved in a capacity upgrade. And at that time, the original treatment tank that was here was totally revised to become just aeration tanks, and new clarifiers were built up across the top. And the control building was added to with another part for the electrical components. And this part was raised because it was discovered at that point that the flood elevation was actually higher. And the screw lift pump station was converted to a screening and a grit removal facility. And so here, just to illustrate some of the innovative work that was done, this here was the old screw lift pump station. Here's the bay for where the screws were. This was modified so that a submersible wet well was put here and submersible pump was put in. It pumped the sewage up to the screens up at the top level of the screw lift pump station, went through the screens when there was one duty screen and one manual bar screen, and then came out a new channel that was built on the side of the building to bring it back to the aeration tank. And along the way, there was a grit chamber right here. So it came out through the screens, out to the grit chamber, and then out to the aeration tanks. And these aeration tanks are modified it used to be the combined treatment with the aeration and clarifier. The clarifier had these benching bits of concrete, and those were saw cut out. And all the horizontal walls that went this way were cut away, and new walls going in that orientation were built. So that aeration tank, 50 years old, been modified considerably. The concrete was sort of at the end, getting towards the end of its useful life, and designed to a very different standard 50 years ago than the standards now for post-disaster requirements. So the original concept of adding a new anoxic tank to work with that tank, it had some questions in it. And in addition, the secondary clarifier that was built in 1996, that would have had to be retained in order to fulfill that concept. And there were even greater problems with retaining the use of this secondary clarifier. First of all, it was a very shallow clarifier in a rectangular shape, and it didn't have good flocculation. So it was more suitable as a primary clarifier really than a secondary clarifier. And in addition to that, it was built in two pieces. There's a construction joint right down the middle. So picture two large concrete structures, and the half that is connected to the aeration or to the RAS pumps in this RAS pump chamber are founded on piles, those red columns there. So they're anchored into the ground going down about 20 meters. But the other half of the tank is just sitting on the soil, and it's connected by a piece of rubber. So in a seismic event, one piece is going to react much differently than the other piece, and it would most likely split apart. So that posed quite a risk in terms of continuing to use this infrastructure. So about 2006, the district undertook a design build expansion. And in that project, the central wastewater treatment plant downtown was decommissioned. It was replaced with a pump station that pumped all the sewage from downtown over to the Mamquam facility. And this facility was upgraded to take a larger capacity. So the green there was the original 1996 era treatment plant with aeration tank and clarifier. In 2006, a new bioreactor was built. That's the yellow concentric circle. Bioreactor around the outside, clarifier on the inside. Back in that era, 2006, the WISR was relatively, the federal legislation that had ammonia toxicity concerns was introduced. And with that concern, this new circular unit was designed to be able to nitrify. That meant the clarifier was built with extra capacity in order to increase the MLSS to have nitrification possibilities. And also that one incorporated a selector zone in the bioreactor. A selector zone is a zone that allows you to create organisms that settle better. So through the use of an anoxic zone, we pick the bacteria that want to settle well and avoid filamentous organisms. And that worked quite well. So like that was sort of a favorable approach to continue to use going forth. But I was in process of describing what happened in 2006. At that point, also a new wet well was put in, a much deeper one. The original one was very shallow, and it caused sewer backups out in the system when there was high flows. And a DAF unit was put in to thicken the waste activated sludge with a centrifuge, and that was in this rectangular building. And also the screening and grit was twinned. And this is just showing the decommissioning of central pump station, the central treatment plant with the placement of a pump station, pumping it over to the Mamquam plant. So I mentioned that creative engineering was used back in 1996 to take a screw lift pump station and turn it into a screening facility, but that meant it was very difficult to expand that in 2006. So some clever engineering was done, and what happened was at the end there's a grit chamber up at the top, and the flow went through the bars and then went to a flow split box up at the top left-hand corner rectangle is a flow split box. Took a portion of the flow out to the new grit chamber, which fed the new circular combined treatment unit, and the old one came by extended channel back to the original plant. And then in subsequent years, there was other upgrades done. Or I should say the last one, this upgrade was done by a design build team, Lockerbie Stanley. And it was rated for 9,000 cubic meters a day. So just comparing the footprint, I wanted to highlight that the new yellow is 9,000 cubic meters a day versus the green there, which is 6,900 cubic meters a day. So it just shows some differences in footprint using sort of superior technology, deeper tanks, the selector technology. So then a number of other upgrades took place, done by various consultants. District put out RFPs for each project, and whoever got it, did it. There was headwork screening, screen replacements, centrifuge replacements, and twinning, and UV disinfection. So now going back to the preliminary design work of the scope that I got involved in, we did a geotechnical review, did some boreholes, and also reviewed the old boreholes, geotechnical information from the past, and pretty consistent as with the past. There was liquefiable layers within the site, 2 of them that in an earthquake situation would sort of turn into mush and it would cause settlement. This was known before, but back then the design codes were not as tight. And so there really wasn't ground improvement that was done. But at this stage of the game where the codes really require very small crack allowances in the concrete, we have to go to a ground improvement to get the reduce the movements that we need to incorporate. We did a seismic investigation of all the existing structures. So that meant looking at each structure and predicting how much it might move and predicting what might be the consequence of each structure. That involved looking at the layer of liquefiable depth under each structure, as well as the distance of each structure from an open face. So those were the factors that determined how much movement there would be. So just to, and that information was summarized, and we identified some high-risk buildings. The existing rectangular clarifier was one of those high-risk items. So to summarize the pre-design findings, the concept of adding the anoxic tank to the old train, it really wasn't a good path to go down. We'd also looked at process intensification rather than building anything at all, just taking the old tanks and putting in some media in order to get to higher treatment capacity. And that really wasn't a good idea either because of the vulnerability of the existing facility. The recommendation was to actually build a new concentric bioreactor and clarifier. The plant was pretty happy with how that one was operating, and they were familiar with it, and it seemed like a good option to undertake. And that new construction would have ground improvements in order to make it seismically resilient. But we identified that it would be possible to take the existing secondary clarifier, rectangular one, while it wasn't performing very well as a secondary clarifier, it was built and it was paid for, and it could be relatively easily adapted to become a primary clarifier. And in doing that, we could get a low-cost way of extending the biological treatment capacity. We would remove roughly 30% of the BOD using an existing tank. And that wouldn't require aeration to degrade that BOD. And that settled solids could then be centrifuged directly. And primary solids dewater much better than secondary solids. So that would actually improve the dewatering of the solids, reduce the amount of polymer required, and give a higher solids content cake in order to reduce trucking costs. So this would be a low-cost way, recognizing that there is still the seismic risk. So we brought that to the district for consideration and discussion, and in the end, they were favorable towards that approach. And the blower building project, part of this project. It actually came about originally in the scope of work. It came out as, the reason for it was that the district had done another side study, and that consultant had suggested that replacing the blowers with more efficient ones, high-speed turbos, might be a good idea. So they just kind of threw that into the project here. But with the things that we were discovering, it really wasn't a necessary thing to do. We were going to decrease the air loads by implementing primary settlement. And there was also a lot of air that was being wasted in the channels, the conveyance channels. If we just turned that off, we wouldn't need the extra air. And the existing blowers, they were, while they were old, they were still in quite good shape. And there was no driving force to go and replace that. So in consultation with the district, we decided to defer that part of the project. And we also developed a long-term plan to phase out expansion of how the plan might grow in the future. That's kind of an important thing to do, to kind of look at the long-term growth beyond just what we're upgrading now. So we developed a concept with new primary tanks. So the adapted primary was just meant to be for temporary usage until they could get enough funds to build a new primary system. And in the long run, more of these combined treatment units would be built out, and new influent pumping would be built, and screening here, and solids handling. So this was sort of a high level assessment of what could be done to build out the plant in the future, given the site that was available. And the district took that and said, thank you, we appreciate that. And then, I guess in the words of Robbie Burns, the best laid schemes of mice and men go off to rye. There was another group within the district that had a different project that they were looking at, building a new administration building. And the different groups were working together, and they decided that this was actually a very good place to build a public works building. And just due to the hierarchy of staff involved, this project kind of had to give way to accommodate that. So the locations were just rejigged a little bit to allow the space for a public works building there. The people on the wastewater treatment team, the owners people, and our team, we were a bit beside ourselves at this stage, but this is what happened. So we just went on with our project to try to build out what we had. And as part of that work, we looked at the district's existing data, and we realized that it was all grab samples. So we asked the district to grab some composite samples. Just some words for operations people. If you're trying to get data to design a plant, the grab samples are really not that useful. Grab sampling is like, taking a sample every 24 hours, or it's probably even less than that. But imagine taking a trip across Canada, going from Vancouver to the West Coast, to the East Coast, and you've got your eyes closed, and like you're one time during the trip, you're asked to open your eyes and give a report of what the topography of the trip is like. And that's sort of what grab sampling is like. Composite is a little bit better. It's like opening your eyes once every hour and getting data to report what the trip across Canada looks like. But it's better than once. We collected some data, and then we took the loadings. We calculated the loadings and divided that by the population at the present time, and then got unit loadings for each person and projected forward into the future at what the population would be using the unit loadings to come up with future loadings. And we did some modeling to look at the impacts of implementing this temporary primary tank conversion, and saw that the duration of this expansion could be extended much further in the future if this primary was taken. So then at the completion of detailed design, we thought about the schedule and sort of the sequencing of what would need to be done. Some of the items of equipment had quite long delivery times, and we wanted to compress the construction schedule. We also considered the impact of contractor markups and owner control and decision-making in the purchase of equipment. We decided to pre-purchase some of the long lead items, the secondary clarifier mechanism, the septic receiving station, the ground improvement contract, and also a rotary drum thickener. The design for this project, the bioreactor clarifier, was done in 3D design, and we had 20 years of operating experience from the plant for the existing one. And the operators had input into what things they liked and what things needed, suggestions for improvement on the old ones. Largely, there were things around access, ease of maintenance, and avoiding confined space entry. So as part of that, there was a permanent stairway designed to go down into the tank with openings in between the barrier walls so that staff could get down in without having to do confined space entry and like all that stuff that's required with it. Monitoring, having a guy sit up top with rescue ropes, all of that was eliminated. Also, the anoxic zone, selector zone, was replicated here with improvements in the design to make that even better. Walkways were put all the way around the center to give easy access. Launder covers were put into the clarifier to try to reduce the amount of algal growth and cleaning required. And so there considerable discussion happened between operations staff and the design team on this. So just that sort of a big picture view of what's going on. The headworks building over here, or actually over in this area, was expanded. Flow went to this secondary clarifier, which was converted to a primary, and then out and around on the red line to a flow split box, which split the flow to the old biological train, or the 2006 biological train, and the new one that will be built. And then comes back out of this and back out to the UV system, and then out to the outfall. The septic receiving station is also just done in 3D design with input from operations on how to make it easy to operate, self-operating, and also with odor control. There's a biofilter, a wood chip style biofilter located here. Provided some architectural renderings so the owner could get a glimpse of what it would look like. So the ground improvement contract was done last summer. The district went out for RFPs and selected a contractor to engage on that. This happened during a period when there was cement availability issues, so that made it a little bit slower, but the contractor did quite a good job of doing this proficiently. The design of the ground improvement was a low strength concrete honeycomb structure that went down about 20 meters. This is using a deep soil cement mixer device. There's a number of options for doing ground improvements, and we looked at various ones. Our geotechnical consultant did quite a good job. We looked at other things like stone columns, but because of the nature of this soil, it was very silty. Some lessons learned from like other projects. Silty soil doesn't work well for stone columns. Like Langley put in millions of these stone columns, and they just didn't consolidate the soil because of a silty nature. So we went straight to a concrete type solution. The soil cutter mixture machine goes down into the ground and cuts a big path and injects lean mixed concrete on the way down and on the way up. And this long probe is used for sampling the concrete column that was created. The strength tests were done. And then on top of all of that, a load transfer platform, like a lean concrete mix platform, was set on top of the honeycomb grid. And this would become the working foundation of the new structure that would be built. So that was all done by fall of last year. And then the main construction contract went out for tender, actually RFP process. And there were 8 bids received. All of the bids were over the budget the district had. There was inflation and the supply chain issues that were happening. This one, it was over by about 40%, which was not as bad as some other projects for the district where projects were over by 200, 300%. But in any case, the project shortlisted the 2 deemed best proposals and started to negotiate with those ones to come up with a scope that could be doable. And meanwhile, at that point, the district had just been notified of a grant announcement, but they were told privately that they were eligible to receive the grant, but they couldn't be announced and no awards could be made. So this further delayed the actual award process. And during that time period, we looked at some redesigns to try to optimize the design and reduce some costs. And that went into contractor negotiations for scope reductions and price improvements. And finally, a construction contract was awarded once the grant agency said, okay, you can do that. And that happened just last month in August. Oops. Sorry, so just some lessons through this project. One, that plant history, retaining the knowledge of old improvements and records and just understanding of what happened at what period and why. That's very important, that awareness, and often it can be lost, and that sort of leads to new projects being oriented without like a understanding of the past. Historians and politicians would say, you need to know where you've come from, you need to know the past, otherwise you're doomed to potentially recreate problems of the past. And they say that in history on a large scale. That also applies in municipal infrastructure. You need to know what has happened in the past and why in order to plan for the future. And continuity of owner, staff, and consultants, that's also very important, understanding what has happened and in order to chart a path forward. Another point is that concept investigation and thoroughness, and really thinking through what you're going to do and what will be done in the future. That's quite important in order to define a project that is well thought out. And long-term thinking and planning is quite important. And I know most of the people here are probably operators, and you don't necessarily get involved in that, but at the larger organizational level, that's quite important to take operator input and also take advice, thinking long-term, what's going to happen. Another point is that post-disaster requirements are becoming increasingly important in infrastructure, particularly critical infrastructure like wastewater treatment plants and water treatment plants. And the regulations and codes are becoming more and more stringent around that. And that needs to be considered and in the awareness of the project team that's planning the project. And the codes are changing all the time and getting more stringent. Regulatory concerns are also important. You have to dialogue with your regulator to find out what implications might be come across in improvements. And granting grants, if you're planning on getting grants, you also need to be aware of how that might affect your timeline. If you do get a grant, it'll probably mean that you can't move ahead until that's announced, and then until all the other details are worked out. You can't even make an award because that would jeopardize your grant. Another thing to think about is the pros and cons of pre-purchase of equipment. It has some advantages, and it also has more work that's required. on the team side and some other complications that can come up regarding the contractor responsibility doesn't have sole source responsibility. And finally, bear in mind that things change, regulations, people, design codes, market conditions, and all you can do as a project team is do your best, try to think ahead of what might go wrong and have mitigation plans for that. And when things do go wrong, just kind of smile and not get too grumpy and work with each other and try to move ahead in the best way possible. So I'm happy to answer any questions that people have.
Hi, great presentation,
Thank
great project. My name is Brian Bedford. I'm with Municipal Affairs, and I'm one of the timeline problems because I administer the grant program you're talking about. So I have a point of clarification to make. And I'll get to in a second. We have had challenges with our federal partner on timelines. Those are out of the province's control. We do advocate regularly to move them along faster, but it's not about announcements, it's about approval. You can't go forward with a contract before approval. You can, once approved, sign that contract, put the shovels in the ground and move ahead. You don't have to wait for the announcement. That ends up being a local government choice or a First Nation community choice. The announcement doesn't dictate when you can go ahead with the project. It's the federal approval that sets your eligible cost date. So once you've got that approval in place, don't worry about when that announcement is coming. You can go forward with the project. Okay. Project timeline is that. Project timelines, grant program timelines are up front at the application end. We try to keep people informed. Communities can ask at any time. We give them updates, but the critical piece is the approval, not the announcement.
Thank you for that clarification. And actually, I probably used the wrong word. It was the approval that we were waiting for, or that the owner was waiting for. I recognize that there's different parties within the granting agency, and one moved much quicker than the other. We were aware of that. Yeah. Thank you for moving quickly on that one, on your part.
So I was just wondering about the lift station going up to the screenings. So how, like, when you said that there was chance of backup into the system and everything,
Yeah.
How much deeper did you have to go, and what sort of redundancy do you have in that?
Yeah. Sorry, let's see if I can. The original lift station was the one that I showed off the screw lift pump bay. That one wasn't very deep. It was only about 3 meters deep. The other one that was built in 2006, that one was about 7 or 8 meters, so considerably deeper.
So how high are you looking at the screening?
About 10 meters, something like that.
Any more questions in the room? Do you have any online? No? I guess I'll just ask one. So the septic screening, they put in one screen or two?
One screen. It's actually a combination unit. It's a rock trap and a screen together.
And then obviously it'll get plugged from time to time and they can just bypass.
Well, it's a self-cleaning
Okay.
screen and self-cleaning rock trap.
Yeah.
So it's continuously cleaning itself
Okay.
out.
Okay.
Yeah.
Great. All right, we are, doing good for time, just about noon. So everyone, if you could please join me in thanking, sorry, it was Raymond. Thank you, Raymond. And everyone online, I believe we're back at 1 p.m. after lunch. So we'll be back here at, it's either 1 or 1:15. I'll be here at 1.